Okay, well, I'm going to try and make a video that will help you guys with position versus time and velocity versus time graphs. Didn't really get a good video today in class because I was doing demonstrations, so I went and stayed after school and I made some videos of the tracks and the cars. And we're going to go over two different examples to kind of get an idea of what you should be doing to try and make these kinds of graphs. And we're gonna assume that you're using a motion sensor and a car, and that you're trying to create position versus time graphs, and then using the position versus time graph, come up with what the velocity versus time graph should look like for that particular arrangement. So the first example we're going to use today is one in which the car is going to be placed in one place and the detector in another, and we're going to try and get the motion of the car as it moves along the track. So here is the video. So as you saw in the video, the car is given a push right here. It travels from here all the way up to here, where it stops. Now, of course, I touched the car at the end, but we're only interested in the moment the car leaves my hand at the bottom and when it naturally comes to rest at the top. So let's watch that video one more time so you can see exactly what I'm talking about in the video.
That's right.
So if we consider that we have a track with a detector and the car starting here, but the track itself is inclined this way. When we first start observing the car has a velocity in this direction. That's the initial velocity of the car. But the car is going to travel from the bottom of the track all the way to a point just before the detector where the car has a velocity that is 0. So this location, remember the detector, is the positive direction. So this location right here is where the car starts. So I'm using a V to represent the velocity and an X to represent the position. And the position initially is far away from the detector, but just before it stops, it is right up close to the detector. So those kind of represent where the car started and ended and what the car's velocity was. But remember, from the vantage point of the detector, this is the positive direction. That's because of the way the detector works. You can only see the stuff that's in front of it. So let's first consider how we would draw a position versus time graph. So I'm going to write out the word position here because all axes have to be labeled with units. So there we go. And our origin represents 0 on the position graph and 0 on the time graph. So at time 0, was the car close to the origin or far away from the origin? It was what I would say is as far as it's going to get. So because of that, I'm going to place a dot on the position graph as far as I can get. Representing at time 0, the car is far away from the origin. Now, we don't know how long this lasted. It was a second or two. I was going to mark here. This is sometime in the future. So if this represents time 0, then this represents the time at the end of the interval. At that moment, the car has moved backwards along the number line that represents where the car is. But time has passed, so I need to go over here to where T is and recognize that the car now is in this position at this time. Remember, this is a position versus time graph, and it's cataloging where the car is at every moment in time. Now That gets us 2 points. Now we have to try and figure out how to connect these 2 points. So the next question I suggested that you ask yourself is the car going fast or slow? Is it going towards the origin or away from the origin? Because the slope of a position versus time graph is the velocity. So what we're trying to figure out is what is the slope of our curve at this point, and what is the slope of our curve at this point. That way we can connect them. Well, at time equals 0, the car is over here and had a velocity in that direction. That means that the car had a big velocity towards the detector. For every other moment that the car moves, all the time that it's spending going here, the car is slowing down. So this is as big as the velocity is going to be, and it's negative. So that means that at this point, it had to have the position versus time graph had to have a slope that was negative and steep. Now, we advance to here. Well, here the velocity is 0. Since the slope of the position graph is velocity, at this point here, since it has to match to have a slope that is a velocity of 0, the slope at this point has to be 0. Because the slope of the position graph is velocity. So now I have 2 points, and I know the slopes at both points. So my job is to choose a smooth curve to connect the 2 points. And that smooth curve represents the position versus time graph. Now, what we're saying here is that the car started here, that far away, and then after a few seconds, it was closer. After a few seconds, it was closer and closer and closer and closest. So as time passed, the car kept getting closer and closer and closer, but it was slowing down. So if we consider a time here in the middle, when the car was moving, and say it was right here, an arrow representing the velocity would be shorter than this arrow, but not 0 because it's still moving. Well, now it's time for us to create a velocity graph. So velocity. Got to label my axes, place the units. Here we go. The velocity graph has to be informed from the position graph. They have to be in agreement. And we say that there has to be continuity between your 2 graphs. They both represent the same events, so they have to tell us the same things. But remember, velocity is the slope of the position graph. Now, we know stuff about the velocity. We know the velocity was biggest at the start, and we know it was negative because it was going towards the detector. That's represented here with a negative slope. So this slope is negative. So when I have to choose my point for where my velocity begins, I need to choose a point that is negative. But I also need to choose a point that's the biggest negative number. So I'm going to pick here. That's the biggest negative number that I have on this graph. It's actually V0 if I want to label it. If I want to put a negative here to remind you that it's in the negative side, that's all just fine. Now at the end of the interval, the velocity is 0. But I need to mark the interval, and these need to be the same because they represent the same amount of time. So t should be the same distance away from the origin on both of these because they represent the same amount of time. So what am I going to do? I'm going to put a dot at v equals 0. The velocity is 0 at this moment in time. And although this doesn't have to be true for everything we're doing for the next couple of days, the velocity graphs will always be linear. There we go. Linear. All right, so I've created a velocity graph. And a couple of reminders. The slope of our position graph is velocity. One of the things I said that we should be doing is considering what the meaning of slope and the meaning of area is. So to further that end, when you're considering the slope of a graph, one thing you should do is see whether the slope and area has any meaning. So slope, to kind of get an idea of if it has meaning or not, one way to do that is to look at the units of the axes. On the position graph, the position side is in meters. That's the vertical axis. And the horizontal side is seconds. That's the horizontal axis. So to consider whether the slope has meaning, you take the vertical axis units and you divide by the horizontal axis units. So the slope of a position versus time graph will have units of meters per second. So if you had never seen a position versus time graph before, and I had never talked to you about them, the slope would have units of meters per second. And if you knew that meters per second were speed or velocity, it was likely that the slope of the position versus time graph was going to be speed or velocity. Now, when we talk about area, area is the portion of the graph between the curve and the horizontal axis. To see if the area has meaning, you multiply the vertical axis units by the horizontal axis units. So meters times seconds. Now, if you know something that's measured in meter seconds, it is possible that this graph is telling you that. If you don't know anything that's measured in meter seconds, then the area doesn't mean anything to you. And just so you know, the area of a position versus time graph doesn't really have any meaning, but the slope does. Now we could talk about the same thing with the velocity graph. The slope of the velocity graph would have units of, we'll start with what the units of the vertical axis are, meters per second, and we will divide by the units of the horizontal axis, seconds. That's meters per second, or meters per second squared. That is the units of the slope. Now, I've already talked about what the slope of a velocity versus time graph means. It means acceleration. These are the units of acceleration. But let's consider the area. The area for this graph would be the area bounded in that section. Now in that section, I take the units from the vertical axis, meters per second, multiply by the units of the horizontal axis, seconds, and this gives me something in meters. Lots of things are measured in meters. Distances, lengths, displacements, positions. It is possible that the area of a velocity versus time graph might have something to do with displacement or distance. Maybe something about what the car did. And we're going to get into that more tomorrow, but we're trying to become people who can get information from graphs. So, in looking at this example, one thing is for sure. Our car slowed down over the interval, right? It started with a negative velocity, and that velocity went to 0. However, it should be very clear to you that this slope is positive, right? Slope, rise over run. This is a positive slope. So even though the velocity was negative the whole time we're observing the car, the velocity was negative. The slope, which now we know means acceleration, the acceleration was positive. What does that mean? it means the acceleration pointed this way, because this is the positive direction. And when you think about what the acceleration does, the acceleration is trying to change the velocity. So the velocity pointed this way, the acceleration pointed this way. The acceleration is trying to change the velocity, trying to make it smaller, trying to slow the car down. All right, let's try another one. So I'm going to produce another situation. So here we see the video. I have changed the track so that it is inclined the other way. And I'm starting the car on the same side as the detector. And you see the direction the detector points, so I made the positive in the direction that the detector points. So here's the video. Okay, so we are clearly watching the car move up the track and back down the track. So if we were to annotate this a little bit, the car is starting here. This is our initial position for the car. Car travels up the ramp and comes back down. So let's get back to the beginning and realize that I give the car an initial velocity this way. Now, just before the car makes it back, so say right there. Oops. Right there, before my finger touches it. We're just about the same distance away. Right? That's where the car is, but the car is clearly going this way now. Right? This is the final velocity of the car. So we want to try and come up with what the position versus time graph would look like for this arrangement. So here we go. So time equals 0 on my position graph, and time equals 0 is this portion of the axis right here. That's the time equals 0 part. The car is very close to where the detector is, so it's close to the origin here. Remember, this is our positive direction, and our car traveled up the ramp and then came back down. So the end of the interval is just before it makes it to the detector. But the end of our interval is the point like right here. Our car traveled this way, then came back and came back to here. So I'm going to put the car right there. At time 0, the car had a velocity this way. So that's a clear velocity. It was a big velocity because it started fast, and it was away from the detector. So I need to have a indicator for my slope that is positive and away from the detector. Now the car, as we just said, traveled all the way up here and came back, and just before I stopped it, the car was going this way with a final velocity. Well, that velocity is negative. It's towards the detector, but it's probably big. So I'm going to put a little mark here to indicate that my velocity was negative. Now again, we want the simplest smooth curve that connects these two things together. So that's the simplest smooth curve that connects those two things together. And notice the car continuously traveled away until such time that the slope of my position graph is 0. That means right around here, the slope was 0, the car stopped. And now the slope is negative, so the car's coming back during this time. All right, let's come over here and do the velocity graph now too. So label it, put my units. And remember that it's supposed to be the same time interval. Now again, the slope here becomes the points here. So the slope is positive. So I want a positive point on the graph that represents the slope. The slope was positive and was big, so I made a point on my graph that is positive and big. It's large compared to my axis. It's far away from 0. At the end of my interval, though, my slope is negative and big. So my slope becomes the point that shows that the velocity was negative and big. My velocity graphs are going to be linear for the time being. So now grab my straight edge, connect these two together. What does this tell us about the motion of our car? Well, about the same. It tells us that at some point or another, the car had a velocity of 0 and stopped, but then went back the other direction because the velocity became negative. What else did it tell us? It tells us something about the acceleration, because the slope of this graph is the acceleration. And this line has a negative slope the entire time, which means the entire time the car was moving, the acceleration was this direction. So this negative acceleration both slowed down the car and sped it back up. When the car had a positive velocity, the negative acceleration slowed it down. And then when it started going the other direction, when it had a negative velocity, the negative acceleration sped it up. It made the velocity more negative. If I go one step further, this area is above the axis, so that area would be a positive area, suggesting the car made a positive displacement. Well, that's right. The car went from here to here. That's a positive displacement. Here, the area is negative, suggesting the car had a negative displacement. Well, yeah, after it made it here, the car went this direction. That's a negative displacement. I hope this helped, guys.